going to talk about optimizing compact difference schemes for high-order CFD using Kokkos. High-order schemes are extremely attractive for turbulence-resolving CFD because they offer spectral-like accuracy with narrow stencils. However, porting... Pull it a bit closer. Oh, sorry. Is that better? Okay. So, however, porting these methods to modern hardware presents three distinct challenges. First, there's the algorithmic challenge. Compact schemes are mathematically local but computationally global. They require solving tridiagonal systems that are inherently serial. The classic Thomas algorithm, while optimal on CPUs, simply cannot exploit GPU parallelism. Second, we face architectural challenges. We need platform-specific implementations, which leads to duplication of code and effort. We usually need platform-specific work distribution strategies. And third, there's the numerical challenge. We need verifiable precision under aggressive compiler optimizations like fast math, FMA reordering, and GPUs introduce non-deterministic cache coherence effects and heterogeneous memory models that can corrupt our carefully constructed high-order accuracy. The key insight here is that accuracy, performance, and portability are fundamentally distinct challenges that require different solutions. So in order to extract performance out of GPUs without compromising precision, we adopted three design principles. The first is algorithm and execution redesign. We introduced parallel solvers for tridiagonal systems. Specifically, parallel cyclic reduction is explored against Thomas algorithm in this work. And we batch line solves so that thousands of tridiagonal systems are solved together in a single kernel-launch. This helps amortize kernel-launch overhead and exposes enough parallelism to actually saturate the device, which turns out to be absolutely essential once we move to time-dependent PDEs. The second is hardware abstraction. We use Kokkos as our hardware abstraction layer. This gives us a single source implementation that compiles for multiple backends. We developed everything locally using OpenMP and serial backends and then validated on HPC systems, which I think was the Kokkos' biggest advantage for us because our GPU usage for this entire project currently is still under 100 node hours. And the third is continuous verification. We use manufactured solutions with known analytics answers, unit tests that verify hardware precision, and end-to-end PDE tests, and everything is integrated with Google Test for automatic regression detection. We tested a total of 13 numerical schemes spanning both explicit and compact formulations, first to sixth order explicit and fourth and sixth order compact schemes. For the compact schemes, we implement and compare both the traditional Thomas solver and the parallel cyclic reduction solver, which allows us to isolate algorithmic effects from hardware effects. So we carefully account for boundary treatments using both explicit and asymmetric closures because boundary handling can dominate error behavior in high-order methods. I want to briefly explain our validation framework. We use 5 problem types: the Laplacian operator with analytic solution, 1D and 2D Burger's equation using both manufactured and exact solutions, a 3D heat equation with a Gaussian pulse, initial condition, and the 2D isentropic shoe vortex as a long-time nonlinear stability test. Grid sizes range from 16 cubed up to 1024 cubed, which is about 1 billion points. The convergence plots here show the Laplacian results. You can see second through sixth order slopes in both L2 and L infinity norms across all tests, all backends, and both solvers. We get machine precision agreement and expected per scheme accuracy. Full convergence reports are in our AIAA 2026 paper. All performance results were obtained on Purdue's RCAC clusters. For CPU and HIP runs, we use Bell, which is a dual-socket AMD EPYC processor, and AMD Radeon Instinct MI50 GPUs with 32 gigabits HBM2. For CUDA runs, we use Gauchi, which has NVIDIA H100 GPUs with 80 GB of HBM3. Both Thomas and PCR solvers were benchmarked on all three backends. I was going to harp on about the hardware, but I'm just going to skip that. Today, I will present the performance results for the 3D heat equation with a Gaussian pulse initial condition and Dirichlet boundary conditions using a sixth-order compact scheme with asymmetric compact boundary closures and RK4 time integration. This is a spherical diffusion problem that exercises the full derivative pipeline across all three spatial directions at every time step. For single derivative and the Laplacian, PCR does eventually beat serial Thomas on GPU, but only at very large n. And at n 128 cubed, CUDA is still at 0.92 times, which is below breaking even. You only start to see real gains at n 512 cube and beyond. Once you add time integration, as seen in panel 3, which shows the results for 984 time steps of the heat equation, everything is below breaking even. The kernel-launch overhead accumulates over all these time steps and completely wipes out any algorithmic advantage PCR has over Thomas. The GPU is slower than serial CPU for a real PDE. Okay, so to tackle this, we did try other optimizations first, replacing deep copy with swap, caching temporary variables to avoid repeated memory allocation calls, but none of that helped as much as this, batching tridiagonal calls. For 3D derivatives in each direction, we were looping over k-planes and calling the tridiagonal solver once per plane. That's k-separate kernel launches. On the right is the batched version. We flatten all j and k indices into a single m index, pack everything into one 2D work array, and make a single call for all lines at once. Mathematically, this is identical. The systems are independent, so reordering doesn't change the solution. But from a GPU perspective, the difference is enormous. Even the Thomas algorithm has a huge gain. The bar chart on the left shows the speed up from batching alone for the 3D heat equation at 128 cube over 984 time steps. There are significant gains on all three platforms with both Thomas and PCR algorithm. The bar chart on the right shows that the gain scales well with increasing problem size. The line plots show time per time step. Before batching on the left, GPU is slower than serial at small n and shows barely any speed up even at large n. The kernel launches are laying heavy on every time step. After batching on the right, the time step parallelization speed up is clear and CUDA pulls away decisively. Here, the serial Thomas algorithm baseline on EPIC CPUs is contrasted against batched PCR approach on GPUs. For the single derivative operator, we achieve 189 times speed up on CUDA and 32 times on HIP relative to serial Thomas on CPU. For the Laplacian, we get 295 times speed up on CUDA and 49 times on HIP. Such speed up can change what is computationally feasible. The execution time plots show that both fourth and sixth order schemes scale well. The speed up plots show that we achieve near linear parallel efficiency on large grids. And the computational throughput plots show that we sustain over 100 million grid points per second on CUDA for sixth order schemes. This is high enough to make high order CFD practical using a single GPU. Multi-GPU gains remain to be explored. For the 3D heat equation, at 128 cubed or 2.1 million grid points over 984 time steps, 62 times speed up on CUDA, 11 times on HIP, the same L2 error across all backends throughout, with sustained throughput and gains accelerating once the problem is large enough to saturate the GPU. Here is the concrete wall time comparison. The same 256 cube problem, same 3,933 time steps. OpenMP with 64 threads, 5 hours and 37 minutes. HIP on MI50, 1 hour and 12 minutes. And CUDA on the H100 is 11 minutes. So that's 30 times faster. On NVIDIA, we pushed to 135 million grid points, 15,729 time steps, which finished in less than 7 hours, which is pretty awesome. I would like to close with 3 Kokkos specific lessons from this work. Profiling full PDEs is important, assuming that GPU is faster after benchmarking individual kernels can be misleading. Cross-compiler correctness requires automated regression testing. Accuracy, performance, and portability are distinct challenges, and correctness across compilers still needs to be tested explicitly. It can't be assumed. I would like to add that for this work, we relied on unified memory and were careful enough to avoid correctness issues from incorrect view placement. But as we move to 3D Euler equations with much larger memory requirements, we are starting to notice silent performance hits. For example, silent fallbacks to host DRAM on HIP, and this is something we're actively investigating. Thank you.
Any questions?
So first, thank you very much for the talk. It was very interesting. So I was wondering, because we were showing some of the differences between your application on CUDA versus the HIP machines. I'm wondering how much you could attribute those speed up differences to just like the different characteristics of the machine versus the kernel-launch overhead and the effectiveness of your batching technique.
Yeah, so that's basically the point of the talk was that even though we specifically used hardware that was so drastically different on HBM 2 to HBM 3, you should see an order of magnitude speed up, but we were not seeing that before batching. So basically, yeah, we see a lot of speed up after that, and even though you see speed up using just the algorithmic approach on the unit kernels, but once you do time integration, you stop seeing that, just because of how you're launching and how you're doing your work balance.
Yeah, I guess I was asking more about.
Sorry.
I was wondering more about because you saw at the end, even after the improvements you did with batching, that the speed up you got from the AMD machine was relatively less compared to the CUDA machine. So I was wondering if that was just because of the relative power between the machines versus the effectiveness. Did you notice any differences in the effectiveness of your batching technique between AMD and CUDA?
Yeah, I would say no. If we're only talking about HBM, going from HBM 2 to HBM 3 should be giving us a lot of speed up if we're actually saturating the machine, and H100s compared to MI50s is I think a couple generations different. So I think that would be expected. Thank you.
Thank you.